I'm going to speak about the development of the global greenhouse gas monitoring system. And I want to start from the general notion is, why do we look at greenhouse gases in principle? So what is about greenhouse gases that makes them so important? And I will start from the greenhouse effect. So greenhouse effect is caused by the process where the sun radiation propagates through the atmosphere, is absorbed by the surface, and then infrared radiation starts escaping into the space, but then it meets the gases which absorb and remit in the infrared range, and that causes the warming of the atmosphere. This process is natural. If we did not have the natural greenhouse effect, the temperature of the surface would be minus 18 degrees Celsius, which means that the life would be impossible on the planet. So we owe the natural greenhouse effect the opportunity to actually live and thrive on this planet. It's not a new thing. So the greenhouse effect was discovered in the 19th century, and already at the end of the 19th century, some physical estimates were made that if we double the amount of CO2 in the atmosphere, CO2 is carbon dioxide, one of the greenhouse gases, then the temperature would be 5 to 6 degrees warmer. Did we learn anything from the 9th century? Actually, we did not. Because if we look at what happens currently with the state of climate, we can see that the main greenhouse gases in the order of effect, water vapor, carbon dioxide, and nitrous oxide, are the major contributors to observed warming, according to the report of the Intergovernmental Panel on Climate Change. And we need to understand very clearly that it's the concentration of the amount, or the correct term in metrology is the amount fraction of the gases in the atmosphere which actually controls the warming. Though we discuss the emissions, we discuss the uptakes, we discuss the removals, at the end of the day, it's the amount of the gas which controls the interaction with the infrared radiation. And why it is important to understand is that the main gases which are related to anthropogenic activity, CO2, methane, nitrous oxide, they are also part of the natural cycles. So what we humans do, we do interact with a natural cycle of carbon in the case of CO2 and methane, a natural cycle of nitrogen in the case of N2O. So the natural cycles, when we start interacting with them, are responding. So if we look at the carbon cycle, and you can see it depicted on this plot, you can see that we humans produce emissions in the atmosphere of CO2, and then these emissions do interact with natural uptakes. So about 30% of what we emit is taken up by terrestrial biosphere. And yeah, it's good. It thrives when it has additional CO2. It has a fertilization effect. Another 25% is taken by the ocean. So you can see it on the diagram. And when it comes to the ocean, it's less good because actually CO2 dissolves in water and causes the ocean acidification. So if we look at the whole budget, these are the fossil fuel emissions, and this is how we release CO2. So we take the fossilized CO2, which is in the form of carbon, from somewhere in the ground, and then we burn it. So we basically convert it into the gas and emit it in the atmosphere. About 30% is taken by the land sink, and about 25% is taken by the terrestrial biosphere, and it's only about 50% which stays in the atmosphere. But given the lifetime of CO2 of over 1,000 years, it accumulates. Every single molecule which has been emitted since pre-industrial time is still within its lifetime, it's still hanging in the atmosphere. So you start wondering, how do we actually know about the levels of greenhouse gases? And here is where metrology is super important. We measure. We actually do measure greenhouse gases in the atmosphere. So within World Meteorological Organization, we have a Global Atmosphere Watch program, which exists since 1989. And this program is actually coordinating global network that performs the very precise measurements of greenhouse gases in the atmosphere. And we do need very precise measurements. There's about 140 stations which are participating in the program. And based on these high-quality measurements, we produce annual assessment, which is called Greenhouse Gas Bulletin, where we speak about the global levels of greenhouse gases. And we also follow the WMO Convention on data sharing, so we make all these measurements openly available for the community. And we started this work back in the 60s. So there was the Global Ozone Observing Network, which was established during the International Geophysical Year. There was in 1967 was the Background Air Pollution Monitoring Network established, BIPM. Then in 1989, they merged together because they were both dealing with atmospheric composition into the Global Atmosphere Watch Program of WMO. And the first measurements and the longest data set of CO2 measurements in the atmosphere was started in Mauna Loa, and the data set starts 1957. So this is the longest data set of CO2 amount fraction in the atmosphere we have. And because we need to make sure that we do understand the changes in the atmosphere, which are pretty small relative to the total levels of the greenhouse gases in the atmosphere, we start coordinating this activity with the first meeting coordinated by WMO in 1975, where we started discussing the measurement techniques and the ways to measure greenhouse gases precisely. And these meetings are happening every 2 years. We call them GGMT, or Greenhouse Gas and Related Trace and Measurement Techniques. And you can see the picture from the last meeting, which took place in 2024 in Brazil. So the greenhouse gas community is growing, the number of stations are growing. But you need to make sure that you can compare that. And to make sure that you can compare that, we establish at those meetings, we establish recommendations on the network compatibility. And network compatibility is a concept which is not usually used in the metrology community, because you measure in the lab, you are interested in the uncertainty of individual measurements. So this is not the uncertainty of individual measurements. The network compatibility is a concept which says what is the maximum bias you can tolerate between any two given stations within your network. And why do we need this? As I said, we are after the trends, and the trends are, let's say, for CO2, it's about 2 ppm per year at the level of 420. And you want to understand those trends reliably and across the globe. In geographical gradients on the background conditions of about 1 ppm. So you need to be able to measure precisely these small gradients and trends in time at the global scale with 140 stations participating. And here we have the traceability, we have the central calibration labs, which keep the primary standard for the whole network. So we make sure that everybody are getting traceable to the same primary scale. We don't use individual standards. We use the whole scale, which is a set of 5 to 7 standards for different gases that are supported by central calibration labs. But we also wanted to make sure that whatever we use as a scale is robust. And as Robert said, we sign the MRI with CIPM to make sure that the scale which is used by the global network is actually consistent with the primary standards which are provided by metrology labs. And you can see on the plot the ongoing comparisons for long-lived greenhouse gases, and you can see that actually the consistency between the different realization of the scale and different standards is actually improving. So we know that the scale which we use to support the global network is consistent with realization which are provided by the metrology community. And again, metrology community does not work with the scales. Metrology community works with primary standards. So we had a long discussion between the atmospheric community, which uses the scale, and metrology community, which uses primary standard. And we come to the conclusion that probably we need to have it more systematic and have a scale comparison more systematic. And for that, the new task group, which is dealing with greenhouse gas scales, was formed under the gas analysis working group. So there's been a lot of progress in that direction, and we actually managed to catch some biases in the WMO scale, while the authorized lab was performing the comparison on behalf, or participating in comparison on behalf of WMO. So given that we have the whole metrological traceability and high quality of the measurements, what do we see with the global levels? So these are the plots of the global trends. So this is a global average amount fraction, dry amount fraction of greenhouse gases in the atmosphere. You can see CO2, methane, and N2O. And guess what? There's no surprise. All of them are showing the positive trend. The amount fraction is growing. And we saw new records, and every time we go to the press conference, we say, it's an old news, the concentration or the mole fraction increased again. So, and again, and again. And you can see that the lower plot show the growth rate, which is an annual increase from year to year for the main greenhouse gases. And you can see that in the case of CO2, the growth rate is increasing as well. So for other gases, we had kind of a strange pause in methane in beginning of 2000s, but then in 2007, the growth started again, and we suspect that these are different processes which drive the regime of methane before 2007 and after 2007. And you can see that the third most important greenhouse gas, nitrous oxide, is also increasing, and the growth rate is also getting higher and higher every year. So let's get into the details of CO2. What happens with CO2? As I said, the growth rate is increasing. So 2023 was the 12th consecutive year when we had an increase of more than 2 parts per million. So these are the growth rates. If we analyze the increase within a year, not from year to year, but within a year, in 2023, we had one of the largest increases because at the end of the year, there was a phase of El Nino, which is usually associated with increased concentrations of CO2 or increased growth rates due to suppressed uptake of CO2 by the biosphere, related to droughts, as well as direct biomass burning, which contributes directly with the growth of CO2. And you can see on the lower plot where you have a geographical distribution that there are some peaks, and in particular, there is a peak of the increase, so this is a growth rate. There is a peak of increasing growth rate in the areas where there was a substantial contribution from the biomass burning in Canada. And that is also confirmed by the measurement of carbon monoxide, which is also co-emitted when you burn something, whatever you burn. So you can see that you can see that there is a substantial increase of the carbon monoxide in the northern latitudes. And that was actually the worst burning season in wildfire season in Canada, which produced in global, so globally there was 2.4 picogram of carbon produced during this burning season, which is 16% above the average. And that actually shows that we need to be pretty careful by relying on the biosphere for the mitigation actions. As I said on the previous slides, the biosphere is responsible for the uptake of 30% of CO2. And when we do our strategies for mitigating climate change, we somehow rely that the biosphere will do its job, which it may not do. First, it's getting drier and warmer, and the biosphere is just burning. And when it's burning, it's releasing CO2 in the atmosphere. It's not sequestering anything. But even if it is not burning, we have an example on this plot, which is coming from the ICOS network, where the measurements of CO2 were performed or are continually performed in Europe. And then they looked at the deviation of the average seasonal cycle versus the seasonal cycle in 2022, then there was a drought in summer in Europe. And what you can see, the red triangles show how much CO2 was left in the atmosphere during the growing season because of the suppressed photosynthetic activity. It was just too hot for plants to photosynthesize. So they were respirating, but not photosynthesizing. So relying on the biosphere is a very tricky thing, and we need to actually make these measurements to understand what biosphere is doing. Otherwise, we just rely on something which is not there or which is not working. If we put the current levels of CO2 in the historic perspective, this is also becoming very interesting, because the current levels of CO2 which we have in the atmosphere are the highest at least for 800,000 if we compare direct measurements, because you can go 800,000 years back by using the small bubbles of air trapped in the air core, in the ice core, and you can measure them with the same techniques as you measure currently in the atmosphere. But if you use all the different priors, it's the back 3 to 5 million years when we last seen such levels of CO2. And at that time, there was 2 to 3 degrees warmer, and the sea level was 10 to 20 meters higher than today. That's the equilibrium state of climate. And what we are doing now, in the geological perspective, it's an instant. So within an instant, we increased the amount fraction of CO2 in the atmosphere by 40%. This is a pretty cool geological experiment. The problem is that 3 to 5 million years ago, there were no humans. So it's pretty risky experiment which we are running here. So what can we do with this information? If we look at the global averages, it's very difficult to use the global averages to take a decision making. So it's good to know that the global levels of CO2 and methane and N2O are increasing, but what do you do about that? So we need to convert it into something which is useful for decision making. And unfortunately, when we come to the changes in emissions, and what we've seen changes in emissions, for example, COVID. During COVID, there was a reduction in global CO2 emissions by, guess what, 5.4%. It looked like the life stands still. Yeah, we still continue consuming. So this small scale of emission reduction is not visible in global average. So you need to drill down into more detailed distribution of the gases. As well as we have substantial gaps in observing network. So global average is representative for the globe, but you need to convert it into the decision-making stuff. And with this in the mind, we come up with the idea of the Global Greenhouse Gas Watch. So let's use all this information which we accumulated within the research community, the measurement network, the Global Carbon Project, the SOCONET. Let's put it all together, align it with their national strategies. For example, there are global systems which are developed in Europe, which are developed in US, which are developed in Japan. Let's align it with the satellite observations, which are measuring greenhouse gases, and do something which is useful for everybody. And how do you do that? So you need to collect all the different observations from satellite, ground-based, metrological, some additional data. Then you need to get information about what we call prior fluxes, which means that what is my knowledge, what is my best knowledge of the biogenic emissions from the forest, and what is my best knowledge of the ocean uptake, and what is my best knowledge of the anthropogenic emissions. So then you put it all in a mixture, do the data simulation, and you produce the gridded fluxes, the gridded net fluxes of CO2, methane, and N2O. So that's the ultimate objective of the system which we are developing. And then from there, you can do a cascading of all the different applications. But you will do the basic. It's like you wanted to produce a bread, you need a flour. So that would be a flour to produce a lot of different downstream applications. What is the core here? You need to exchange the data. If you sit on your data set, and don't exchange it with anybody, and do it differently from everybody, the value of your data sets is diminishing. And what kind of observations do you need to wire there? You can use the flux measurements, which are very good if you wanted to understand really at the level of the processes. So if you wanted to constrain your biospheric models, you will do the flux chamber and get the emission factors. Or you can get a little bit better emission factors with a better representation if you do the flux measurements, direct flux measurements using eddy covariance towers. Or if you wanted to have a big footprint and see what the atmosphere is doing, you would put the atmospheric concentration measurements or atmospheric amount fraction measurements at the tall tower, and that will give you the footprint of tens of kilometers. And you start wondering that the traceability chain in all these measurements will be different. Oh, we have an animation. so this is how the product would look like. So you would have a dynamics of the distribution. This is an example for CO2. That shows you the amount fractions of CO2 in the atmosphere. You can do it backwards. That would give you the fluxes. And you can use these products for multitude of different applications. So you can use this model, you can use this modeled graded data to, this is funny, so I don't want to go forward. So as a boundary condition for national, urban, and facility scale, I can press backwards, and that gives you the decision relevant scale where you have information for decision makers on the national scale or urban scale or facility scale to actually take action and see and track if the actions are making sense. So this system, we call it Global Greenhouse Gas Watch, was endorsed by WMO Executive Council. We start now with implementation, pre-operational phase, which means we need to set up the whole framework, how we're going to do that. And for that, we hosted a data provider workshop. So we looked at what do we have. So we set up the requirements for the modeling system. So we agreed that the target would be 1 degree resolution. So it's 1 by 1 degree resolution or 100 by 100 kilometers. Especially, we are talking about the weekly fluxes, which are produced with 1 month latency. So within 1 month, you would get the flux for the previous month and the 3D concentrations with a daily latency. And we also mapped what kind of data do we need to make the system work. And that includes, as I said, in situ data, satellite data, in situ ocean data. And we discuss how do we exchange this data, what is the role of coordination in different domains. It seems that the satellites are well coordinated. The ocean community is also well coordinated by SOCONET. There are some questions about the coordination within the in situ atmospheric community and remote sensing, as well as the role of the data aggregator. Who can actually send the data in WMO information system, because you don't want to introduce biases which are connected to one individual measurement station. So, and on the side of post-processing, we also made substantial progress. So we developed the good practices for the urban application. There is 31 examples which are included in this document. And these are 31 ways you can do that. And again, if you look at the traceability chain will be slightly different in all the different cases. And we're developing the same for the national scale application, which we will discuss in June this year. So the way forward, so where do we go from here? First, we definitely need to ensure that the current observing system within different domains are sustained and existing data are shared. And there are some risks. We know in the current world there are some risks to the sustainability of the observing systems, and we need to make sure that those are sustained and that they are traceable and the data are exchanged. But as I said, we need to extend the observing network in the data sparse region. For example, tropics are not observed. ocean, 3% of the ocean is observed, while ocean is taking up 25% of CO2. What happens if the ocean stopped doing that? How would we know where did it happen and how did it happen? So, and all those measurements need traceability. They all need traceability, they all need quality assurance. We cannot just deploy thousands of low-cost sensors and pray that they produce the measurements which can constrain 2 ppm fluxes and annual differences. That's not going to work. We need pretty good traceability in those cases. We also need to educate the community how to use those data-driven data sets, because what we've seen, inventory is saying, okay, this is part of my job, I just do the calculation, I calculate the emission factors, statistical data, I report, that's it. I'm not interested in what you're telling me. And then there is a substantial 2-3 times difference between what you report and what we see in the atmosphere. There is a problem. So we need to actually communicate how do we address this problem, how do we make the data which are used for decision making consistent. And of course, it all needs a lot of partnership on national and international scale. And I'm really honored and I'm really happy that WMO did establish a partnership with BIPM. We are all benefiting from them. And congratulations to all of you. Thank you.